Welcome to E-Pathshala lecture series in computer science. This course is on operating systems, and for the past few modules we have been looking at process synchronization and solutions to the different synchronization problems. In today's class we will learn about some classical problems of synchronization, and we will see how solutions to the problems can be given using semaphores. So, we have been seeing about cooperating processes, and we know that cooperating processes share data, and the data that is being shared can be in the form of variables or in the form of data structures, and many processes which share data or which share common variables need to have synchronization between them, and synchronization between processes is achieved using different ways. It can be achieved through synchronization hardware, it can be achieved through semaphores. So, we have seen how synchronization is being achieved through synchronization hardware and semaphores. And in today's class, we will see how these classical problems of synchronization are being solved using semaphores. There are a number of classical problems of synchronization like the bounded buffer problem, readers and writers problem, and dining philosophers problem. And these problems can be used to model many other concurrency control problem or many other synchronization problem that arise in different situations. So, whenever a new solution to a synchronization problem is devised, then they try to apply it on these classical problems of synchronization and check out if that synchronization solution works well for this particular kind of problem. And if it is working for these problems, then it should be able to apply to many other kinds of problems as well. So, first we will learn about this bounded buffer problem. This problem actually we had seen earlier in an earlier module, and we tried to give a solution a different way. Today we will see how solution is given to this problem using semaphores. So, in this bounded buffer problem, you have a pool of n number of buffers, and each buffer is capable of holding one item. And there is a producer process who is capable of producing items, and the producer places the items in the buffers. And there is another process called the consumer process. The consumer consumes the items from the buffers, and the producer will have to wait when all the buffers are full. So, when all the buffers are full, there is no place for the producer to place the item, and hence the producer will wait. And when the buffers are empty, then the consumer will wait because there is no buffer which has got item, the consumer cannot consume any item. Now, this is the problem. The problem is that you have a common buffer which needs to be shared between the producer and the consumer process. So, we will see how this common buffer is being shared between producer and the consumer. So, why is synchronization needed in this kind of situation? That is, you have a common buffer which should not be accessed at the same time by the producer as well as the consumer. When the producer is placing an item in the buffer, that should be done atomically. Very similarly, when the consumer is consuming an item from the buffer, that has to also to be done atomically. So, how is this done? We have a solution here using semaphores, and 3 semaphores are maintained named the full, empty and mutex. We saw in an earlier class that a semaphore is nothing but a shared variable. That variable's initial value depends on how many number of processes can access the resource that the semaphore is guarding. So, the semaphore is used to safeguard one particular resource, and the initial value of the semaphore should be set accordingly as to how many processes can access this particular shared resource. So, here we have full, empty, mutex, 3 shared resources, and this mutex semaphore, it provides mutual exclusion for access to the buffer pool. So, any process, be it the producer or the consumer, before accessing the buffer will have to wait on the semaphore mutex, and after accessing the buffer they can signal the semaphore mutex, and initially it is initialized to 1. Why is it initialized to 1? Because only one process can access the buffer at a particular time. So, mutex is safeguarding this buffer pool, and only one process can access the buffer pool, and hence the initial value of mutex is set to 1. And now we have two more semaphores, the empty and the full semaphore. The empty semaphore actually is used to count the number of empty buffers. It is initialized to n. Initially there are n number of empty buffers, that is all buffers, all the n buffers are empty, and hence the initial value of empty semaphore is set to n. And then we have another semaphore called the full semaphore. In the full semaphore, it counts the number of full buffers, that is it tries to maintain a count of how many buffers are full. Initially no buffer is full, the producer has not placed any item in the buffer, and hence all buffers are empty, and hence the initial value of full semaphore is set to 0. Now we will see the algorithm for the producer process. So, the producer produces an item in a variable called next p. This next p is a variable that is local to the producer process, and then it waits on the empty semaphore. The empty semaphore initially is set to the number of empty buffers. So, all the buffers are empty, and hence empty will be set equal to n. So, wait on n will actually decrement the value of n, and hence the producer process can continue. Then it will wait on the mutex semaphore. The mutex semaphore is again initialized to 1. So, if no one else is using the buffer, the producer process can decrease the value of mutex, and it can move on to adding this item that it has placed in the produced in the next p variable to the buffer. And then after placing the item in the buffer, then the producer process signals mutex, and signal of full is executed, that is full value will be incremented by 1. Now see the algorithm for the consumer process. The consumer will first wait on full, then it will wait on mutex, then it will remove an item from the buffer to next c. Next c is a local variable for the consumer process here, and then it will signal mutex, and then it will signal empty, and finally come out. And we will see what is the implication of this algorithm. So, the producer process has to place items in this buffer, and the value of full is equal to 0, the semaphore full is 0, the value of empty is equal to 4, and mutex is equal to 1. And what should the producer execute? If you look at this algorithm for the producer process, it will have to first wait on empty semaphore, and then wait on mutex semaphore, and then it will place the item to the buffer, and then after placing the item it should signal mutex and signal full. So, first it should wait on empty, then wait on mutex. So, what happens when you are applying this wait on empty? It finds that the value of the empty semaphore is 4. So, it will decrement the value of the semaphore by 1, and the value of the semaphore becomes 3. So, the producer wants to place an item and it executes. So, see what happens. So, the value of empty becomes 3, and the value of mutex was earlier 1, and when you execute wait of mutex, it will decrement the value of mutex to 0. So, empty becomes 3, mutex becomes 0, and one item is placed in the buffer. The producer places an item in the buffer, the item is placed in the buffer. And next what happens? Full is made equal to 1. So, after placing the item in the buffer, what should the producer do? It should signal mutex, it should signal full. So, full is made to 1 and mutex is also made to 1. So, this is what happens at the end of one round of the producer algorithm, that is it first waits on empty, decrements the value of empty, then waits on mutex, decrements the value of mutex, then places the item, and then it signals full and signals mutex. Now, if the producer wants to place the next item, again it should wait on empty, wait on mutex. So, what happens? It waits on empty and empty becomes 2 and waits on mutex, mutex becomes 0, and then it places the next item. The next item, item 2 is placed in the buffer. And what happens to the full semaphore after placing the item? Full becomes 1 and it should be incremented, full becomes 2 and mutex becomes 1. So, now the second item is placed and all semaphores are updated. And now, if the producer wants to place again the next item into the buffer, it will have to wait on empty, wait on mutex. So, it is 2 and 1 currently, it will change to 1 and 0. So, empty becomes 1 and mutex becomes 0. Producer places the next item, then item 3 is placed into the buffer. So, now what happens to full? Full should be signaled. Signal full is executed, it becomes 3 and mutex is signaled, that also becomes 1. And similarly for item 4, after item 4 is being placed, your empty is 0, mutex is 1, full becomes 4. Now, in this case, if the now all the buffers are full. So, after all the buffers are full, if the producer wants to place another item, we will see what happens. The producer have to wait on empty, then wait on mutex, then place an item. If it tries to execute wait of empty, it will find that the value of 0, empty is 0. So, the producer will wait on the semaphore empty. Unless the value of empty is incremented, this producer cannot continue, it will be waiting, it will keep on waiting on semaphore empty. So, we see that the producer waits on semaphore empty. Now, we will see what happens if a consumer wants to consume an item. So, now we see that all the buffers are full and the consumer now wants to consume an item. So, what is the algorithm for the consumer process? The consumer will actually wait on full and then it will wait on mutex, then consume the item. After consuming the item, it will signal empty and signal mutex. So, we will see when it tries to remove the first item, it waits on full. So, it decrements the value of full. Semaphore full is decremented by 1, it becomes 3. It waits on mutex. So, the value of mutex is also decremented, it becomes 0. Now, the consumer has to consume an item, it had consumed one item, item 4. And again if it wants to consume the next item. So, what should happen? It should again wait on full and then we should wait on mutex and it should signal empty after consuming. So, after consuming the first item, it has signaled empty and the value of empty has become 1. It has signaled mutex, the value of mutex also has become 1. Now, before consuming the next item, it should wait on full and wait on mutex. So, the value of full should become 2 and the value of mutex should become 0. So, similarly, it can be done for the other items. Now, finally, when all the items are consumed, the value of full becomes 0 or the value of the semaphore full becomes 0 and the value of this semaphore empty becomes 4. And now, after this, if the consumer wants to consume an item, it cannot consume the item because it will be waiting on the semaphore full, which is currently 0. So, here we see that the solution to the bounded buffer problem is being given using semaphores. They have used 3 semaphores and this mutex semaphore will actually look at when this is being accessed. Okay. So, before placing an item or before consuming an item, the producer will have to wait on mutex as well as the consumer will have to wait on mutex. and after producing the item the producer will signal mutex, and after consuming the item also the consumer will signal mutex. And these semaphores, empty and full, they are used to maintain the count of the number of buffers that are full and empty respectively. And now we go to the another problem which is called the readers writers problem. So here there is one data object which is shared between a number of many concurrent processes, and these concurrent processes can either be reader processes or writer processes. Reader processes are the ones which can read from that data and they do not write or do not perform any updates. But the writer process, they can both read as well as write. And the problem here is that you should not allow multiple readers to read at the same time, but multiple writers should not be allowed to write at the same time. Only one writer can access the shared data at a particular time, and writer should have exclusive access to this shared object. And there are many variants to the solutions to this readers writers problem. You have a first readers writers problem as well as second readers writers problem. In first readers writers, the solution will be like the higher priority is given to reader process, the writer process are given low priority. And the second solution, a high priority is given to writer process and second priority is given to reader process. And here we will learn or we will look at the solution that is given for this first readers writers problem, where you give priority to readers, that is in the sense when readers are reading, no writer is allowed to write into the file. Only when there is no reader that is reading, the writer can write into the file. And at a particular time only one writer can write, more than one writer cannot write into the file. So, we will see a solution where they maintain two semaphores, mutex and WRT, and they also maintain a variable called read count. And initially this mutex is 1, WRT is 1 and the read count is 0. And this WRT is a semaphore that is common to both the readers and the writers. Before they try to access the file, the readers as well as the writers, they will have to wait on this WRT semaphore. And you have a read count variable, and before manipulating the read count variable, they try to access this mutex semaphore, and after manipulating they signal the semaphore. Basically, the read count variable is being safeguarded by the mutex semaphore. And we look at the solution, the algorithm that is given. This is the writer process, the algorithm for the writer process. The writer process first waits on WRT semaphore, then it will write, and then finally after writing it will perform signal. And so, see, look at this example, you have a file. This file is the one that is to be shared between readers and writers. Now, there is no one which is accessing this file, and initially the value of mutex is 1, the value of WRT is 1, read count is 0. So, what should the writer do? The writer should wait on WRT, then write into the file. After finishing writing, it can signal WRT. So, when it waits, executes wait on WRT, the value of 1 becomes 0 and the writer can write. And after writing, what it should do? It should increment the value of WRT and it can exit. So, this is how the writer's algorithm will work. Again, if it wants to access after it finishes writing, then it will, you can see that it will signal the value of WRT and exit. The value of WRT becomes 1. So, initially it was 1, then it waits on WRT, makes it 0, access the file, and then finally it becomes 1 after signaling WRT. Now, we look at the reader process, the code for the reader process, the algorithm. The reader process maintains a count, a variable called read count, which actually maintains the number of reader processes who are currently reading from the file. As I told you earlier, there can be more than one reader process which can access the file at a particular time. So, you need to maintain or need to remember how many number of reader processes are currently accessing the file. So, for that this read count is maintained. So, initially the process, the reader process will wait on this mutex semaphore which is safeguarding this read count, and then it will increment the read count, and if read count is equal to 1, then it will wait on WRT. What is the case when read count is equal to 1? When will read count be equal to 1? It will be equal to 1 when the first reader is trying to read. So, when the first reader is trying to read, it will also check if there is anyone else who is writing into the file at a particular time. If a process is writing, then this reader will not read, it will just wait. Only after the writer finishes off, the reader will continue to read. And then it signals mutex. And basically, you have the semaphore mutex basically because this read count is a variable which can be accessed by many reader processes. The same variable is accessed by many reader processes, but you do not want many people to access that read count variable at a particular time, at the same time. So, you try to give access to this read count using this mutex semaphore, and then reading is performed, and then again after finishing reading, the process should decrement this read count saying that it has finished reading, one reader is going out, and read count becomes 0 if this is the last reader process, because read count will become 0 when everyone has finished reading, there is no reader process. And if this is the last reader process, it will signal WRT as well, because it had done a wait of WRT first time and then it will signal WRT, so that maybe another reader or maybe another writer can come and read or write the file. So, finally, it will signal mutex because it had waited on mutex here, and then it should signal mutex because it has manipulated this read count variable. We will see how reading can be done from a file. So, initially you have this mutex semaphore with WRT value equal to 1, mutex equal to 1, read count equal to 0, and the first reader arrives. So, the first reader changes the value of mutex to 0 and it increments the read count value, and because read count is equal to 1, it waits on WRT, the value of WRT becomes 0. And after waiting on WRT, it makes value of WRT equal to 0. Now, it signals mutex because it has manipulated read count. Then reader 1 reads the file. So, the situation now is that mutex value is 1, WRT is 0, the read count is 1, reader 1 reading the file. Suppose reader 2 arrives, and reader 2 also wants to manipulate this read count variable. So, it waits on mutex, increments read count and signals mutex. Now, it does not have to wait on WRT because it is not the first process, read count is not equal to 1, it is the second reader process. So, it can directly go start reading the file. So, reader 2 reads the file. And now there are two processes, reader 1 and reader 2, both are reading the file. So, the values of mutex, WRT and read count will be like mutex is 1, WRT is 0 and read count is 2. And now a writer process arrives. So, the writer process will have to wait on WRT and then write and then signal. But now when it executes wait on WRT, it finds that the value of WRT is 0 and hence it waits on that semaphore, it will not write now. Unless reader 1 and reader 2 finish reading, it cannot write. Now, say reader 1 leaves. When reader 1 leaves, it will change the value of mutex equal to 0 because it has to decrement the read count and decrements the read count. After decrementing, it will change mutex to 1. It is not the last reader, read count is not equal to 0, so it just leaves. So, reader 2 is now reading the file, and there is one writer 1 who is waiting, still waiting, and the value of mutex is 1, WRT is 0, read count is 1. Now, say reader 2 also leaves. Reader 2 will have to decrement the read count, so it changes the value of mutex to 0, decrements the read count to 0, and now because read counts become 0, it will have to signal WRT because this is the last reader. It will have to signal WRT, increase the value of WRT semaphore so that the writer can write after this reader process leaves. And reader changes mutex to 1 because it has changed the read count value. So, now the reader has left, there is writer 1 who is waiting, and the values of mutex is 1, WRT is 1 and read count is 0. Now writer 1 is waiting on WRT. So now it can decrement the value of WRT and make it to 0 and writer can write. So writer 1 is now writing. So we have seen now that how the reader process were reading. So when multiple reader processes arrive, they can be allowed to read at a particular time. Only the read count is maintained to know how many number of readers are reading. But if the writer arrives, even while there are a number of readers who are reading, the writer has to wait. Only after all the readers finish, the writer can continue to write. So the value of mutex, WRT and read count is 1, 0 and 0 now respectively. WRT is 0 and the writer is writing. So if now a reader arrives, what do you think will happen? Now a reader arrives, a writer is writing. Now what happens? It will have to, maybe it will decrement mutex, it will change the value of read count, increment the read count, but it will execute wait on WRT because it is the first reader who is arriving, read count will be equal to 1. When it executes wait on WRT, it will have to wait for the writer process to finish off because the value of WRT is 0 and wait of WRT will put the reader to the waiting state. And only when the writer finishes writing, it will signal WRT and it will let the next reader to read. And suppose while this writer is writing, if a writer arrives, the writer is writing and another writer arrives. Again what will happen? The writer will wait on WRT, the value of WRT is 0, hence the writer cannot continue to write, the second writer will keep on waiting. So this is how the solution to this reader's writer problem has been given. Now we have another problem called the dining philosopher's problem. So this is a very interesting problem where you have a number of philosophers who are sitting around a table and are dining. So they have a bowl of say spaghetti and they have to use the chopsticks which are placed to the right and to their left. So each philosopher will have to use the chopstick to his right and to his left, and only using both of them he can dine. So but a philosopher will not keep on dining always. He will dine for some time, then place down the chopsticks and then think for some time and so on. So when one philosopher places the chopstick down, the neighboring philosopher can pick up that chopstick and he can use that for dining. So the problem here is that you have this chopstick which is a shared resource between the different philosophers and they have to use this common shared resource. So how a solution can be given to this dining philosopher's problem? So what is done? Each chopstick is associated with a semaphore. So if there are 5 chopsticks, there is a semaphore for each of these chopsticks. So each chopstick has a semaphore that is guarding it. And you define an array of semaphores called chopstick of I. And initially all the values are 1. Why all the values are 1? Because the chopstick can be used by only one philosopher at a particular time, or that is a resource which can be used by one process at a particular time. So the algorithm for any philosopher will look something like this. So initially the philosopher before dining will have to wait on this chopstick. Maybe he will have to wait on the leftmost chopstick and then he will have to wait on the rightmost chopstick. So if he will have to wait on chopstick of I, then chopstick of I plus 1 mod 5 because it is you are looking at only 5 number of chopsticks, and then eat, and then after finish dining he will have to signal chopstick of I, the leftmost chopstick, and then release the rightmost chopstick. So this has to happen for every philosopher. For every philosopher this should be the code. So he will first wait on the leftmost chopstick and then on the rightmost chopstick, dine and then signal the left and the right. But the problem here is that this can lead to a deadlock. So what can happen is that, say every philosopher, if they try to dine at the same time or eat at the same time, so all will try to lift up the leftmost chopstick first and then they will try to wait on the rightmost chopstick. Now all will have one chopstick which is the leftmost chopstick, but the rightmost chopstick will be held by the neighboring philosopher, and because it will be his leftmost chopstick. So, all philosophers will keep on waiting continuously, and this may lead to a deadlock kind of situation. But this situation can be solved by many other solutions. Many other solutions are given in literature. So, with this I conclude this day's topic. The summary is, we have seen a number of classical synchronization problems like the bounded buffer problem, the readers writers problem and the dining philosophers problem, and we saw how solution to these problems are given using semaphores. References is, and you have the acknowledgement. Thank you.